Hi, I'm Roxanne Martin from Mr. Farrar's Period 3 Calc AB class, and today I'm going to teach you about revolutions. We all understand the concept of integrals, using infinitely many rectangles to find the area under a curve. Well, with revolutions, we're going to do something really similar. This solid is being rotated around the x-axis, resulting in an approximation that would resemble a lot of circles, kind of the same way that the integrals are infinitely many rectangles. So a revolution, we're going to use infinitely many circles. With an integral, we integrate the original function to find the area. So the notation looks something like this. With a revolution, we're going to integrate the area to find the volume of the solid that we are creating when we revolve. So those infinite circles I mentioned before, this is where we see them. That r squared, pi r squared, is the area of a circle. What we're trying to do here is integrate the area to find the volume of the solid that we're creating. Now, there's an r in our equation, but there's no r in an x and y plane. R is going to be the equations creating the solid we are rotating. So there are two types of objects we're going to get by rotating these solids. One is disks and the other is washers. The equations for these are virtually the same. The only difference that washers are hollow in the center, so they're going to have an extra piece subtracting that middle portion. So again, we can see the hollow center of the washer with the little radius that is being subtracted from the larger radius. We do this so that the middle hollow piece is not included in the total volume. These shapes can also be shifted. This means that the axis of rotation is not the y-axis or the x-axis, but something on one of the sides of the solid that is being rotated. So this is just going to alter the equation a little bit because now we have to take into account that it's not being rotated around the x or y-axis. So also, since these pieces are being squared, it doesn't matter the order that we write them in. So this general form that I wrote here looks a lot more like the washers, but if we simply get rid of that last part, then it works for a shifted disk. Here's the first problem, relatively simple. So I'm going to draw it for you so that you can visualize the solid that we're rotating. So for this portion A, we're going to be rotating it around the x-axis. So what we're going to do is we're going to take the earlier disk formula that we were given, because this is a disk as it doesn't have anything hollow in the center, and we're going to substitute in the values of the equations that we have been given. For part B, we're going to be rotating it around the y-axis. This is a little bit more complicated because first of all, we have to make sure it is in terms of y. This is a very important and a very common mistake. Make sure everything is in terms of y for these problems. Also, it makes it a little bit more difficult because now we're going to have two radiuses. So this is now a washer because there's a slightly hollow portion in the center. So you can see I found my larger radius and my smaller radius, and now I'm going to write it out and simply fill it into the washer equation we were given. So I'm going to draw this out again just because this is a lot easier if you can visualize it, especially visualizing the rotation helps a lot. But for part C, we're going to do y is equal to 5 for the axis of rotation. So we're rotating this up. This is going to be a little bit different than before, but it's still not very difficult. We just have to make sure that we find the correct big R and little r. So that big R is just going to be a straight line, and that's just the value 5. And then the little r is going to be that 5 minus x. So here, it doesn't matter if I wrote x minus 5 or 5 minus x, because since we're squaring it, it is going to end up being the same. So fill it into the equation, and there we go. Okay, so for part D, we're going to have x equals 7 as the axis of rotation. So I'm just going to draw it out again so that we can visualize it. So this is where our axis of rotation is going to be, and again, whenever we're rotating over a vertical line, we have to make sure everything is in terms of y. So this is a really common mistake, so remember that, in terms of y. Now, so we're again going to find the big R and the little r. It's just the same process for everything. And then this is obviously a washer because it has a big hollow space in the middle since it doesn't ever touch the axis of rotation. So we're going to go through that now, and then once you've found both the big R and the little r, we can substitute it into that original expression that we've been given. So for part E, we're going to have y equals 6 be the axis of rotation. So for this, we get to keep things in terms of x, but it's above the solid that we're rotating, and the solid never touches it, so it's going to be a washer. So again, finding that big R and the little r, and then just going through with the same process of substituting it in to the expression that we were given at the beginning. So for the final part F, we're going to have x equals 5 as our axis of rotation, and since the solid lays against it, it's going to make it a lot easier, and that's going to be a disk. But it's a vertical line, so we have to make sure that everything is in terms of y. That's always going to be important when we have a vertical line. Now, all we have to do is just find the one radius that applies for this rotation. Since it's a disk and not a washer, it makes it a lot easier. So put that in and we got it. So now let's move on to a little bit harder of a problem. Here we're going to have two functions as the things that define the solid. And let's just keep it simple-ish and rotate it about the y-axis. So I'm going to draw this just because we really need to visualize this. I really recommend always drawing this and graphing it out because otherwise it's really difficult to know what your radius is going to be, especially when you have washers, because you really need to be able to visualize which radius is the small radius and which radius is the larger radius. So drawing it here, it's a little bit tight, but we're going to see that we have one small solid part, and that's going to be rotated over the y-axis. So since it's over the y-axis, we need to put those equations that we were given as the parameters of the solid and put them in terms of y. So that's going to make x squared becomes the square root of y, and 2x becomes y over 2. And then the big R is we're looking at it from the y-axis, so that's going to be that square root of y function. And then the little r is going to be the inner function, which is that y over 2. And then from there, it's the same steps that we've been doing. It's always straightforward. There's no reason to complicate it more. So we have those points of intersection. That's also another thing you're going to have to find, but for the most part, this should be relatively easy to find. So here we're just substituting it in and making sure that everything is squared and that we have a pi out front. There are a couple of mistakes that are really easy to make with revolutions. One of the big ones is forgetting the pi out front of the integral, which is really important because since we're dealing with circles, we have to have that pi constant. Another one is forgetting to square the r, which again is really important since we're dealing with circles. The last one is something that I've mentioned a few times already, but it's when the axis of rotation is a vertical line, so a line where x equals a constant, we have to make sure that all of the parameters are in terms of y and not in terms of x. After watching this video, you should know the expression for disks and the expression for washers, and how to find those and the differences between them. Also, I hope you understand shifts a little bit better so that you understand if an object is shifted to the left or to the right and up or down, and that you can really rotate an object in any direction. So, I hope that this helped, and good job. Thanks so much for watching.